Alright, here we have lecture 3.4, which corresponds with section, I believe, 5.6 from the textbook. This is probably one of my favorite sections in all of college algebra, and that is rational functions. A very fascinating topic, particularly when we start studying limits in calculus. But before we, get that far, we got to ask, what is a rational function? Well, a rational function is a function of that form, r at x equals p at x divided by q at x, where p and q are polynomials. So essentially a rational function, you can think of it as a ratio of polynomials. It's polynomial divided by polynomial, hence the term rational function. Now, as we discussed back in Unit 2, when determining domain, we determine what inputs are going to cause complications, and one such complication is division by zero. So if we look at this example 1, determine the domain of this function f, we know that x cannot equal negative 7. Otherwise it would cause division by zero. So I could plug in any number below negative 7, or I could plug in any number above negative 7. But I cannot pick negative 7 itself, because it would cause division by zero. Now in this second example, r at x, we'd have to go ahead and factor. So we'll factor the fun just for funsies, and then we factor that trinomial on the bottom. That'll factor to 9 and 2. So if we look at this expression, we know x cannot equal negative 9, because that will cause division by 0, and x cannot equal negative 2. Now, you might look at that negative 2 and go, wait a second, is that okay, because don't those cancel out? Well, we'll discuss that in detail later, but if you were to plug in negative 2, you'll get 0 divided by 0. 0 divided by 0 is still undefined. So you can pick any number you want besides negative 9 and 2. So if we were to summarize this on the number line, there's negative 9, there's negative 2. You can pick anything below negative 9, anything in between the two values, and anything above negative 2. So if we were to put that domain in interval notation, that would be from negative infinity to negative 9. That's anything below negative 9. Negative 9 to negative 2, that's anything in between. And negative 2 to infinity, which describes anything above negative 2. So we can determine the domain of a rational function by just asking ourselves, hey, where do we get division by 0? Now that begs the question, okay, what happens at these undefined values? Like, what behavior do we observe nearby division by 0? Well, there's one or two things that's going to happen. You're either going to get a hole or a vertical asymptote. We're going to discuss both of these in detail, beginning with holes. Well, I'm sorry, I take that back. Before we describe that, we need to define what an asymptote is. An asymptote is a line or curve that continuously converges or continually converges to a given function. And there are many flavors of asymptotes. You got vertical asymptotes, slant asymptotes, horizontal asymptotes. You can have nonlinear asymptotes. But in college algebra, we'll only be looking at linear asymptotes. So here's an example of a vertical asymptote, which I'll label VA. So, something like this. So as you can see, this function, let's call it function f, is going to keep getting closer and closer and closer to the vertical asymptote. That's the idea with the vertical asymptote. It keeps getting closer and closer and closer, and you can do it on both sides as well. So a slant asymptote is going to look something like this. So there's my asymptote with a dotted line, and you might have some function that looks like this. So it might curve around and play around for a little bit, but if we lead from left to right, you can note that the function keeps getting closer and closer and closer and closer to the asymptote, and it will never stop getting closer to the asymptote. It will get infinitely close to that asymptote as x moves to infinity. So as we keep reading towards the right, that function is going to continuously converge to the asymptote. That's what makes the asymptote an asymptote. Then you've also got horizontal asymptotes. So there is an example of a horizontal asymptote. So in this case, it's converging as it moves to the left. So as x goes to negative infinity, or in other words, as we keep going left and left and left, from right to left, farther and farther and farther, the function is going to keep getting closer and closer and closer to that horizontal asymptote denoted by the dotted line. So visually speaking, that's what an asymptote looks like. And in this course, I'll be representing asymptotes by dotted lines. Now, if you were to type these functions into graphing software, typically graphing software will not display the asymptotes per se, but you can see that behavior in the function. But just to make it a little easier on the eye, when I'm drawing these by hand, I'll mark the asymptotes with dotted lines so you can really see what's going on. Alright, now that we've introduced asymptotes, we can really return to our rational functions. So let C be any real value that causes division by 0 in rational function R. Like I mentioned earlier, there's one of two things that's going to take place. There's either going to be a hole there, or there will be a vertical asymptote there. So it's crucial that we distinguish holes from vertical asymptotes. So we will get a hole at a particular input that causes division by 0 in a rational function, but no longer causes division by 0 after reducing. So that's how we know we have a hole, is if that division by 0 disappears, so to speak, when reducing, then that means there is a hole there. Now, if we reduce and it still causes division by 0 even after reducing, that's when we get a vertical asymptote. So let's go ahead and study this example here. Now we know that we can't have x plus 3. Now let's go ahead and factor this. Now when you look at this, you got x plus 3 times x minus 3 divided by the quantity x plus 3, and you're like, oh hey, those cancel. This whole thing just equals x minus 3. This is basically a form of reducing fractions, right? This is how one simplifies a rational expression. However, this isn't exactly true. These are not equivalent. Notice, in the original function, I cannot input negative 3. I'll get division by 0. But in the reduced form, if I plug in negative 3, I get negative 6. We have a contradiction there. These two technically aren't equal. They are equal AE. So what that AE stands for is almost everywhere. Almost everywhere. So these two are equal almost everywhere. And we can see that when we sketch their graphs. If we sketch the graph y equals x minus 3, let me go ahead and sketch that real quick. It looks like this. So we got a y-intercept at negative 3, and slope is 1. Just like that. Now, if we go to graph our function, x squared minus 9 over x plus 3, you can actually type this into graphing software if you so desire. It's going to look something like this. Sorry, one second. Let me just go ahead and get my Cartesian plane set up. Still has a y-intercept at negative 3. And then at negative 3, negative 6. Right there. There will be a hole. Now these are exactly the same graph, except the hole. That's the only difference. They're the same exact graph except for the hole. That's why we say those two functions are equal AE, or equal almost everywhere. They're equal everywhere except at that hole. That's because if I look at this function, and I input, say, negative 3, well, if I plug it in, negative 3 minus 3 is negative 6. But if I plug it into this function, you get something that is undefined. And there we have our issue, because we said after reducing, when we reduce, sorry, but we get that. All right, when we reduce, supposedly these two are supposed to be equal. Well, they're technically not equal. They're equal almost everywhere. So that's how you identify a whole. If that division by 0 seems to disappear when reducing, that means you've got a whole at that location. Now if we look at the next example, we know x cannot equal 2, and there's nothing to reduce there. So let's go ahead and study this. So we can't plug in 2, but what happens if we plug in 2.1? And you can type this into your calculator if you want. And if we do that, then we get 10. Well, we can get even closer, right? Instead of 2.1, what about 2.01? Okay, we get 100. Well, what about 2.001? We get 1,000. What about 2.0001? And perhaps you can see the pattern. The closer we get to 2 from above, the y values shoot towards infinity. Now, we can also approach 2 from below. So, what about 1.9? So, if you need to, go ahead and press the pause button, type that into your calculator, you punch it in, and you're going to get negative 10. And what about 1.99? Well, then you'll get negative 100. 1.999, well, you get negative 1,000. What about 1.9999? Alright, so, type that in. And you get negative 10,000. And you can see there, as we approach 2 from below, the y values shoot towards negative infinity. So if we were to look at this visually, we're getting a vertical asymptote at 2. Notice as we approach 2, say 2.1, 2.01, 2.001, the y values skyrocket almost straight up. You can see those as y values are shooting up towards infinity. But as we approach the graph from below, like 1.9, 1.99, we can see the y values shooting downwards. So here you can see very, very different behavior. Very different behavior. So, nice little tip. Holes seem to disappear when reducing, right? That's why you don't see a very big difference in the graph when those values cancel out. It's just a little tiny hole. Whereas the V vertical asymptotes have always caused division by 0. Both in the original function and in the simplified or reduced function. So let's go ahead and do a few examples demonstrating this. So starting with example 1, we got this function f. Let's go ahead and factor everything. So let's factor the numerator and factor the denominator. Now when we reduce, notice those factors cancel. We're left with x minus 2 over x minus 3. So we're going to have a whole at x value negative 2. Notice I cannot input negative 2 into the original function because it causes division by 0. It'll result in 0 divided by 0. But I can plug it into the simplified one. Notice how those factors of x plus 2 canceled out. That indicates a whole. Now if I plug in negative 2, what you do is input that value into the reduced expression. So if we plug that in, so that would be negative 2 minus 2 over negative 2 minus 3, we get negative 4 over negative 5, we get 4/5. So that's where we have a whole. Now let's look at a vertical asymptote. The vertical asymptote is easy. It's just at whatever x value causes division by 0 in both the the reduced expression and the original. Now, notice the different forms here. Notice I'm writing the whole as an ordered pair because it's a point, whereas I'm writing the vertical asymptote as an equation because it's a vertical line. So, beware of the notation there. Now, let's go ahead and look at example 2. We can go ahead and simplify this one. So we can factor out a factor of 3 in the numerator. Denominator simplifies to x plus 6, x minus 4. X minus 4 is canceled, giving us 3 over x plus 6. So we're going to have a whole at 4. Because 4 minus 4 causes division by, causes 0. Now we input 4 into the reduced expression, and we get 3/10. That's where this whole is. And the vertical asymptote is going to be at x equals -6. Alright, cool beans. So that's how we distinguish wholes from vertical asymptotes. And let me just go ahead and add one more example, just to demonstrate something. So if we reduce this, notice, using properties of exponents, that quantity x minus 3 squared, well, those will cancel until it leaves x minus 3 quantity squared in the denominator. So just reviewing some exponents there. Now, notice 3 still causes division by 0 even in the reduced expression. So when it comes to determining wholes, there are no wholes in this expression. But we do have vertical asymptotes at 3 and -2. Alright. Let's go ahead and discuss end behavior. So, end behavior is, the left end and the right end. Basically, as x goes to negative infinity and x goes to positive infinity. So, let's just, do a little bit of numerical analysis. Let's just punch in some numbers here. Suppose I plug in 1. Well, then we get 2 over -4. In other words, -1/2. Now, let's say we plug in 10. So if we plug in 10, that's going to be 101 divided by, 101 divided by the quantity, 1000 minus 5. And just to keep it simple, we'll write these as decimal numbers. So if you punch it in, you get 101 over 995, which is approximately 0.1. Well, let's suppose we plug in 100. So we're just letting x get bigger and bigger and bigger to the right. And if we do that, we get approximately 0.01. And perhaps you can see the pattern here. If we plug in 1000, we get approximately 0.001. So as you can see, the output or y values keep getting smaller and smaller and smaller as x gets bigger and bigger and bigger. That's because we're comparing degree 2 versus degree 3. So a cubic is eventually going to outpace any quadratic in existence. So if the denominator is outpacing the numerator, then you're going to converge to 0. It's going to converge to 0. Even if you go to negative infinity, right? Negative 10 cubed is going to be a far larger number than negative 10 squared. So if your denominator is outpacing your numerator, it's going to converge to 0. So if the denominator is dominant, then the function will converge to 0 as x goes to plus or minus infinity. Now let's look at this expression. So we have 3x squared plus 2x plus 5 divided by x plus 4. Well, let's go ahead and see if what we get when we run the division algorithm. So let's go ahead and do the division and see where this takes us. Alright, so if we do that, alright, so just doing our standard division here, so if I multiply by 3x to get 3x squared, so multiply accordingly, and then divide. So that gets us 2 minus 12x is negative 10x plus 5. So then I'd want minus 10, multiply by negative 10, and subtract, and we get 45. Now notice we can't get x into 45 anymore. We are done. So what this tells us from the division algorithm is 3x squared plus 2x plus 5 divided by x plus 4 equals 3x minus 10 plus the remainder, and the remainder is 45. Of course, the remainder just goes over whatever you were dividing by. So we get that from applying the division algorithm. Now notice right here in this term, denominator is dominant. So that means this is going to go to 0 as x gets larger and larger and larger, which just leaves the 3x minus 10 part. So here the end behavior is 3x minus 10, and we get that from long division of polynomials, which is a prerequisite skill. So if you need to review that, hop on Google and review how to do your long division if need be. But in this case, if the numerator is dominant, we're going to do long division. And this is what we get, what is known as a slant asymptote or oblique asymptote. So there's a supplemental video I included on Folio that includes more examples of slant asymptotes. And I highly encourage you to watch that supplemental video if you need some more practice on these. So in summary, if the denominator is dominant, it goes to 0. So we demonstrated that numerically. And then we can do long division in the other cases, because in the case of long division, we'll get some remainder where and by the very nature of being a remainder, the denominator will be dominant, so the remainder always collapses to 0 as x goes to infinity, and thus we're left with the end behavior. Now this begs the question, do we have to do long division every single time? Well, no, not necessarily. So it's all summarized quite nicely here. If the denominator is dominant, automatically goes to 0, don't have to do any division. And we discussed that, why that is numerically. Now if it's a tie, if the numerator and denominator have the same degree, the end behavior is given by the leading coefficient. Now if you don't believe this, you can do the long division and you will just get the ratio of coefficients, or I'm sorry, of leading coefficients. Now if that numerator is dominant, if the numerator has a higher degree than the denominator, our only choice is to do the long division. So let's go ahead and determine the end behavior. If we look at number 1, we got degree 5 on top and degree 5 on bottom. So we got a 5th degree polynomial in the numerator, 5th degree polynomial in the denominator. So it's given by the leading coefficients. So our end behavior is the horizontal asymptote at y equals negative 3 over 2. So if it's the same degree, it's given by the leading coefficients. Now notice in example 2, in the numerator, we have a 3rd degree polynomial. In the denominator, it's 5th degree. So 3rd degree versus 5th degree. Denominator is dominant. So in other words, the end behavior is going to converge to 0. Alright, and now the last one, notice the numerator is dominant. So this is where we got to do that long division. And here we'll get a slant asymptote. So if I want to get x to x, I'd have to have x. That would give me x squared minus 2x. Subtract and repeat. So that would get us 5x plus 2. So then I want a plus 5. And that would get us a 12 as the remainder. The remainder is inconsequential. End behavior is y equals x plus 5. So if you were to study the graph of this, you would see as x goes to negative infinity, it would converge to that diagonal line. As x goes to positive infinity, it would also converge to that diagonal line. Alright, so here we have a summary of everything. So what we want to do first when studying or analyzing a rational function is we want to go ahead and reduce it. And while reducing it, be on the lookout for any holes. This is where we identify holes. We identify holes as we're reducing the function. Now, to determine x-intercepts are going to be your roots from the numerator. In other words, they are the inputs that cause 0 in the numerator. And just like the previous lecture, if it has even multiplicity, then there will be a bounce. If it has odd multiplicity, then it will punch through. Vertical asymptotes are going to be your zeros from the denominator. And again, this is after reducing. Now, vertical asymptotes also have their own multiplicity. If they have an even multiplicity, then the tails are going to be going in the same direction, either both down or both up. If they have odd multiplicity, then the tails will be going opposite directions, as you can see visually there. And then for end behavior, it's numerator degree versus denominator degree. If that denominator is dominant, then your end behavior is going to be 0. If it's a tie and they have the same degree, then your end behavior will be given by the leading coefficients. And if the numerator is dominant, then you're going to have to go through the long division. And of course, the y-intercept, you just plug in 0 and see what the output is. Now, just a quick tip as you're working through the test review and homework, horizontal asymptotes are associated with end behavior. So if I'm asking you to determine any horizontal asymptotes, I'm essentially asking you to determine the end behavior of that rational function. So let's go ahead and look at an example. So here we have a graph and we need to come up with the equation. Now, we need to identify what type of graph we're looking at, and this is very clearly a rational function. Note the vertical asymptotes. That's a dead giveaway. Right? Nothing else we've studied in this class thus far has vertical asymptotes. So we know that our equation is going to be some rational function. So let's draw that division bar, and I'll put the leading coefficient, which we call a, out front. We'll figure that out last, just like we did for quadratics and for polynomials in the previous lectures. Now our x-intercepts are representative of the polynomial in the numerator. So let's look at our x-intercepts. So we got an x-intercept at 1, 2, 3, 4 at -4. Notice it's a bounce. So if I have an x-intercept at -4, that means I have a factor of x plus 4. Notice that it bounces there, so I need to give that even multiplicity. And then my other x-intercept is at +4, and it goes through. So that means I have a factor of x minus 4, and I'll leave that with an odd multiplicity since the graph goes through there. Alright, and we now have our vertical asymptotes. We got a vertical asymptote at -2. So that means I have a factor of x plus 2. Now notice that this one has odd multiplicity because the tails are going in opposite directions. Now at our next vertical asymptote at +2, that indicates a factor of x minus 2. Notice at this vertical asymptote, the tails are going in the same direction, which means it's a even multiplicity. So don't forget to mark the squaring there, make it even multiplicity. Then our next vertical asymptote is at 5, which means we have a factor of x minus 5. Again, notice tails are going in the same direction, which implies even multiplicity. So that factor needs to have an even power. So make sure you remember that even power. Now, we have the work 90% done. All we need to do is plug in a point. I like plugging in the y-intercept and solving. So let's go ahead and plug in the y-intercept and solve for that leading coefficient. We know our y value is 2 when our x value is 0, just by looking at the graph. And we need to go ahead and solve this equation. So we know 2 equals, that's what, -32 alpha, because that's a 16 times, 16 times 4 is 64, so -64 alpha. And then the denominator, we got 4 times 25 times 2, which is 200. All right. So 2 equals, let's go ahead and reduce that. It reduces down to 8 over 25. So therefore, that implies our leading coefficient equals negative 25 over 4. Alright, so we can now go ahead and write our function. So that's y equals negative 25 times x plus 4, quantity squared, times x minus 4, all over 4. So that's just that leading coefficient. Our alpha's out front, and then I'm just rewriting the rest of the equation we came up with earlier. And there we have it. Alright, so that's how we get from the graph to the equation. So just to summarize on this example, intercepts and multiplicity tell us what goes in the numerator. Vertical asymptotes in their multiplicity tells us what goes in the denominator, and then we input a point to solve for the leading coefficient, which we denoted by alpha. So you notice our strategy here is exactly the same as it was for polynomials in the last lecture and for quadratics in the lecture before that. We get our framework down, and then once we have the framework established, we input a point and solve for that missing coefficient. Now let's try the reverse direction. Let's go from the equation to the graph. Now here we'll have to factor. So that will factor to 5 and 2. So x minus 5, x plus 2. And then we have x minus 7, quantity squared, x plus 4. Nothing here cancels, so that means there are no holes. Our x-intercepts are at 5 and negative 2. Notice they both have a multiplicity of 1, which is odd, so that means it's going to go through. We got vertical asymptotes at 7 and negative 4. Notice 7 has even multiplicity, negative 4 has odd multiplicity. Now if we look at our end behavior, we got degree 2 on top and degree 3 on the bottom. So our end behavior is going to be 0. And if we plug in a x value at 0, we get, let's see here, let's see here, 49 and 4, we get approximately negative 0.05. It's a very small negative number. Alright, let's go ahead and start marking everything. So we got x-intercept at 5, 2, 4, 5, and it goes through. Another x-intercept at negative 2 goes through. So little tiny t's there to remind myself that it goes through. Vertical asymptote at 7, 2, 4, 6, 7. So I'll mark my vertical asymptotes with a vertical dotted line and mark that this one has even multiplicity. And then we got another one at negative 4. Go ahead and mark that one down. That one is odd multiplicity, so I'll go ahead and write that. And what we need to do now is plug in a test point, because I need to know if it's going to start in quadrant 2 or quadrant 3. So let me go ahead and plug in, say 2, 4, and say plug in negative 6. If I plug that point in, stand by, let me go on and compute that. Sorry, typing it in now. We get negative 0.13. So in other words, it's down below in quadrant 3. It's negative. So there we have it. We have our graph started, and I'm just following the vertical asymptote there. Now odd multiplicity tells me that it's going to be opposite. So instead of starting low, it's going to start high. I'm going to go through my x-intercept here, go through my y-intercept, which is right around there. And then I'm going to go through my other x-intercept and ride the vertical asymptote on that. Now this one is even, so that means tails are starting in the same direction, so this one's going to start up high and then ride behavior on the way out. There's our graph. Now it's very, very important that you pay attention to the multiplicity of your asymptotes. Notice at the odd asymptote, tails are going opposite directions. At the even asymptote, or even multiplicity asymptote, they're going in the same direction. Notice I got all my intercepts correct, and notice the only place I touch the x-axis at are at the x-intercepts. So be very careful when you're graphing that the only place you contact the x-axis at is at the x-intercept. So the only place I can touch the x-axis at is at 5 and -2. Let's go and do one more of these. Alright, so last example for the lecture, number 2. So let's see, does anything cancel here? Nothing cancels, so there's no holes. Our x-intercepts are at 1. Now notice that has an even multiplicity, so it's going to be a bounce. The next one is at -3, so it's going to go through because it has an odd multiplicity, power 1. Our y-intercept, so if we plug in 0, we get, let me type it in real quick, 3 divided by -5 times 25, and we get 0.048. So it's a very small positive number. And if you just heard 0.048 there, it's fine. We've got a vertical asymptote at 5. It has odd multiplicity. And at -5, notice it's squared. It has even multiplicity. Now, if we look at the end behavior, we have degree 3 in the numerator, degree 3 in the denominator. It's a tie, so it's given by the leading coefficient at -2. All right, let's go ahead and sketch the graph. We'll go ahead and draw the Cartesian plane here. All right. 6. 6. All right. So x-intercept at 1, it's going to bounce. At -3, it's going to go through. There's our y-intercept, barely positive. Vertical asymptote at 5 and -5. At -5, it's even multiplicity. At +5, it's odd multiplicity, and then we have our end behavior is -2. So here's our horizontal asymptote there and there. Now notice I'm only marking it out at the ends because that's the only place where it matters. Now what's nice about having a non-zero horizontal asymptote is it tells us where to start without having to do a test point. So going from left to right, I cannot put it in the upper corner because then I'd have an x-intercept that's not there. So it has to be in this bottom corner. So even multiplicity tells us the tails start in the same direction. I'm going to go through, hit my y-intercept, bounce off my x-intercept, ride the next asymptote. Odd tells us odd multiplicity, start in the opposite direction, and hey, looky, there's my horizontal asymptote. I can ride it out. So there's a shape of the graph. Now, warning here, this is a rough sketch. It does not have accurate turning points. We would need calculus. We'd have to compute the first derivative to figure out the turning points. But it does have accurate asymptotics and intercepts. And that's what I'm really looking for in these graphs, is making sure you can identify asymptotes, intercepts, and end behavior along with multiplicity. Alright, well that's a wrap. Feel free to read this section in the book, and feel free to start working on that test review, and have a wonderful day.